Hey guys, welcome to our introductory module into the Bronsted and Lowry model. Today we're going to be covering what the Bronsted and Lowry model actually is, introducing you to the concept of conjugate acids and bases, and showing you how amphiprotic species and the Bronsted and Lowry model are related. Before we talk about the Bronsted and Lowry model, it's very important for you to understand a theory that came before it, and that's the Arrhenius theory. So in your chemistry studies, there are three main theories you need to understand. The Arrhenius theory, the Bronsted and Lowry model, which we're covering today, and the Lewis electron model. The third is not that examined, so remember the first two really well. So we'll get stuck in. The Arrhenius theory states that an acid generates a H plus in solution, and a base generates an OH minus. At the very basic level, this makes sense, but like all things, once you dig a bit deeper, the theory breaks down and has some significant limitations. First and foremost, it can't explain why substances such as ammonia, which has a chemical symbol of NH3, and the fluorine ion, can act as bases. This shouldn't be possible according to this theory, as they do not contain an OH group. Furthermore, this theory requires the presence of an aqueous solution, so it can't explain how acid and base reactions occur in gases. Another significant problem with this theory is that it can't explain the relative strength of acids and bases. If all acids are generating H+, and if all bases are generating an OH-, how can you distinguish between strong acids and weak acids, and also strong bases and weak bases? Theoretically, they should be the same. Hence, two clever scientists, Bronsted and Lowry, made up a new model. This came about due to the observation that when an acid and a base react, there is a corresponding conjugate acid and conjugate base. These are two very important terms that you need to get familiar with. The main takeaways, the absolute high yield for your exams, are these 2 points here. So a Bronsted-Lowry acid is a proton donor, so it likes giving protons, and a Bronsted-Lowry base is a proton acceptor, so it likes accepting protons. In previous modules, we've shown the link between a proton, so H+, and the hydronium ion here. So when H+ is put into solution, it reacts with water to give you H3O+. In this way, these two things are equal. So they mean the same things, they're just at different stages. So if you see a H+ or a H3O+, just know that they mean the same thing. But the most high yield points is that a Bronsted-Lowry acid is a proton donor, and a Bronsted-Lowry base is a proton acceptor. So hopefully now knowing what a Bronsted-Lowry acid and base is, we can make sense of this using some worked examples. So in our first one here, we have ammonia reacting with water to form the ammonium ion and a hydroxide group. So what exactly is going on here? In your exams, you'll be given an equation and then asked to find the Bronsted-Lowry acid or the Bronsted and Lowry base. The easiest way I find to do this is just using some pattern recognition. So the first thing I do is look for things that are similar. So the NH3 on this side and the NH4 on this side are similar. They vary only in that the NH3 has gained a H+, or a proton. Another way of saying this is the NH3 has accepted a proton. So the NH3 is a weak base. Similarly, if we use our reasoning for the H2O, we'll get a similar result. So the H2O and the OH- differ in that the H2O has lost a H+. Another way of looking at this is that the H2O has donated a H+. This H+ is accepted by our Bronsted-Lowry base so the NH3. Thus, NH3 is the Bronsted-Lowry base, and water here is acting as the Bronsted-Lowry acid. In our second example, we have nitric acid and water forming H3O plus and NO3 minus. Similarly, just using some pattern recognition, the HNO3 and the NO3 minus on this side look very similar, only in that the HNO3 has lost a H plus. Another way of saying this is not lost, but donated a H plus. So if something is a proton donor, it is a Bronsted-Lowry acid. The H2O then picks up this H plus that we've donated and forms H3O plus. So the H2O picks up the H plus, so it accepts the proton. It's a proton acceptor. It's a Bronsted-Lowry base. In our last example, we have acetic acid and water reacting to form a hydronium and the acetate anion. Similarly, we're going to use our pattern recognition. So this and this look very similar, only in that it has lost a H plus. As we said before, it hasn't lost it, it's just donated it into the solution. And if something is a proton donor, that's a Bronsted-Lowry acid. This donated H plus is then picked up by the H2O to form hydronium. If something accepts a proton, it's a Bronsted-Lowry base. I'll give you a moment to take this in and summarize of the three equations, which is the Bronsted-Lowry acid and which is the Bronsted-Lowry base. Yep, so the Bronsted-Lowry acids are nitric acid, acetic acid, and water. And the Bronsted-Lowry bases are ammonia, water, and water in the last equations. So now that you've understood how to figure out the Bronsted-Lowry acid and a base in a given equation, I'm going to start off by introducing you to the concept of the conjugate acid and the conjugate base. So the first thing I want you to understand is that a parent acid, so Pa, will have a conjugate base. And a parent base will have a conjugate acid. Parent just means the initial reactant. So we have an example over here. So B minus plus H plus reacts to form HB plus A minus. Don't freak out, these are just hypotheticals, right? So clearly, B minus accepts the H and becomes HB. HA donates the H and becomes A minus. So our parent acid is the HA. And the conjugate base is whatever's left over. So that's the A minus. Our parent base is the B minus because it initially accepts the H. And our conjugate acid is the HB. Hopefully that's a little clear. And I'll just reinforce that now. So the parent acid, HA, will donate a H plus as per the model and leave behind a conjugate base, A minus. So parent acid, conjugate base. Conversely, our parent base, B minus, will accept a H plus and leave behind a conjugate acid. Parent base, conjugate acid. Typically, in an exam scenario, you'll be given an equation. We have some worked examples in the next slide, and then you'll be asked to find the conjugate acid and the base. I want you to think systematically. So first, find the Bronsted-Lowry acid and base. These are your parent acids and bases. Then, for the parent acid, you can find the conjugate base, and for the parent base, you can find the conjugate acid. A really easy way is just to know the fact that the conjugate base is a parent acid just without a H. So if you look at the difference between HA and A minus is just HA without the H. And the parent base is just the conjugate acid with a H, which makes sense because it's the H that the parent acid has lost. A high yield association for you to understand for your exams is the strength of the conjugate acid or base. This varies inversely with the strength of the parent acid. So what exactly does this mean? So the stronger the parent acid, so if you have a strong acid such as HCl, it'll give you a really weak conjugate base such as Cl minus. Conversely, if we have a weak acid such as acetic acid, it'll give you a relatively stronger weak base such as the acetate anion. So hopefully that was clear in that what a conjugate acid and a conjugate base is, and now we'll work over some worked examples. So the first thing I want you to do when you approach any problem involving Bronsted-Lowry acids and bases is to find the Bronsted-Lowry acid and the Bronsted-Lowry base. Remember, we use some pattern recognition. So these two things are quite similar, but they vary in that the initial reactant has lost a H+. And I'm going to signify that with minus H+. This negative H+, or the H+ that's lost, has gone to the OH- to give you the H2O. So H3PO4, my bad, has donated a H+ in solution. So that's the Bronsted-Lowry acid, given it to the OH-, which has accepted that proton to form the H2O. So our parent acid is the H3PO4. Our conjugate base is the parent acid without a H or the H2PO4. Conversely, our parent base is the OH-. It accepts the proton and forms our conjugate acid, the H2O. For our second example, don't freak out, stick to the basics. So we look at what's similar. This and this are quite similar, but they have lost 2 hydrogens this time. So if you see that this group and this group are the exact same, it's just that that's been lost. These 2 hydrogens are donated in solution and given to these fluorines to form 2 lots of HF. Hence, our parent acid, the proton donor, is H2C2O4. Our conjugate base, in this case, it's a little bit different. It's not just minus 1 H. It's lost 2 H's. However, the same concept applies. It's still C2O4 2 minus. Our parent base accepts the H+ and is the 2F minus. And our conjugate acid is the 2HF. Hopefully that's clear. Our third example is probably the most obscure yet, but I put this in here just to emphasize that the same principles apply regardless of if the equation looks simple like this one or as complicated as this one. Although it looks deceptively complicated, it is rather simple. Again, we look at what's happening. A bit of pattern recognition shows you that these 2 groups are the exact same, except that that has gained a H+. So where did that H+ come from? These 2 groups also look the same. except that has lost the H+. And I want you to write this. So our parent acid, the proton donor, is HClO3. Thus, our conjugate base is ClO3 minus. Our parent base is the proton acceptor. So bear with me, so a little long. Thus, the conjugate acid of the parent base is this here. Hopefully that's clear now. So far, you've learned what a Bronsted-Lowry acid is, what a Bronsted-Lowry base is, the difference between conjugate acids and bases. Now, it's important for you to understand amphiprotic species. These are substances that can act as both proton donors and acceptors. Another way of saying this is that an amphiprotic species is something that can act as both a Bronsted-Lowry acid, so the proton donor aspect, and a Bronsted-Lowry base, the proton acceptor part of this. For the context of your exams, these are usually weak acids such as carbonic acid, acetic acid, and water itself. You'll likely get a question on amphiprotic species in the context of buffers, which we'll cover in a separate module. But today, I'd just like to introduce you to the concept. So now we'll see an amphiprotic species in action. An example is HCO3 minus. So when placed in water and in the right circumstances, it can donate a H plus group to the water to form H3O plus and CO3 minus. However, in the right circumstances as well, it can also accept a H plus from the H2O and form H2CO3, and the water forms an OH minus. So HCO3 minus acts as both a proton donor and a proton acceptor. Hence, by definition, it is amphiprotic. A very high order association for you to understand is, when I talked about the right circumstance, this is what I mean. To make an amphiprotic species behave as an acid, it requires a strong proton acceptor or a catalyst. To make it behave as a base requires a strong proton donor. So these two are the right circumstances in which an amphiprotic species will either act as a proton donor or a proton acceptor. That influences, if you think of it as kind of a crossroads, the circumstances being these two influence which way the amphiprotic species chooses to go in. So hopefully now you have a pretty strong understanding of what an amphiprotic species is. It's important for you to understand how to identify an amphiprotic species when you see it. Usually, especially typically in the context of your exams, there'll be the anion of a acid dissolving in water. So you have H2PO4 minus, which is the anion of phosphoric acid when it dissolves in water. Another example would be HCO3 minus, which is the anion of carbonic acid dissolving in water, or HSO4 minus, which is the anion of sulfuric acid dissolving in water. These are all examples of amphiprotic species. Don't forget, water itself can also act as an amphiprotic species. As I stated previously, you can think of the actions of an amphiprotic species as kind of like a crossroads. when presented with a strong proton donor, such as HBr, it'll act as a base, and when presented with a strong proton acceptor, it'll act as an acid. So now we'll write the equations for both. So we have H2PO4 minus, don't forget your states, plus HBr reacts to form. So it's going to act as a base, so H3PO4 plus the bromine anion. Conversely, it can also act as an acid when presented with a strong proton acceptor. So once again, H2PO4 minus, don't forget your states, reacts to form. So this time, instead of accepting a proton, it actually donates one more. So in this way, amphiprotic species can act both as an acid and base, depending on the circumstance.